Close your eyes for a moment and let yourself drift toward the water. The ocean is waiting for you, patient, ancient, endlessly deep. It has been here long before us, and it will be here long after. And tonight, we're going to spend some time getting to know it. Let's begin at the very beginning. When the Earth was young, impossibly young, nearly 4.5 billion years ago, it had no oceans at all. Just rock, heat, and chaos. But slowly, over millions and millions of years, water vapor escaping from within the Earth itself began to cool and fall as rain. It rained for a very, very long time. And that is how the ocean was born, not in a single dramatic moment, but gradually, quietly, like something that simply had to exist. Today, that ocean covers nearly 71% of our planet's surface. More than 2/3 of everything you'd see from space is water. Earth isn't really a rock at all, it's an ocean, with a little bit of land resting on top. And that ocean isn't just wide. It's almost unimaginably deep. If you were to take the tallest mountain on Earth, Mount Everest, standing nearly 9 kilometers high, and place it gently into the deepest part of the sea, it would vanish completely beneath the surface, with more than a mile of water still above its peak. The deepest known point in the ocean is called the Challenger Deep, tucked within the Mariana Trench in the Pacific. It plunges nearly 11 kilometers down. Humans have visited the surface of the moon more times than they have visited that place. Which tells you something rather wonderful. We know more about the surface of the moon than we do about the bottom of our own ocean. About 80% of the ocean floor remains unmapped and unexplored. The sea holds more mysteries than the sky. There is so much still to discover, still sleeping in the dark. And oh, how dark it gets! Sunlight can only reach so far into the water. The uppermost layer, the sunlit zone, stretches down to about 200 meters. Below that, the light begins to fade and thin, until, by around 1,000 meters, there is no sunlight at all. Just permanent, velvety darkness, stretching all the way to the bottom. Most of the ocean, by volume, exists in that darkness, in a perpetual quiet that you and I will likely never experience. And yet, it is not empty. Life finds a way, even there. But before we venture into the deep, let's rest here for a moment in the shallower waters, where the ocean breathes and moves. The ocean is never truly still. It's always in motion, pulled by the gravity of the moon above it. The tides you see at the shore, rising and falling twice a day, are the ocean responding to the moon's gentle tug. The moon, nearly 400,000 kilometers away, is close enough and heavy enough to reach across space and stir the sea. High tide and low tide, an eternal rhythm, a conversation between the earth and the sky. The water itself travels even further than you might expect. Deep below the surface, vast rivers of water move through the ocean in what scientists call the global ocean conveyor belt, a system of currents that circulates water around the entire planet, carrying warm water toward the poles and cold water back toward the equator. One complete journey around this conveyor belt takes roughly 1,000 years. The water you're imagining right now may have last been in the Arctic a millennium ago. And woven through all of this water, from surface to seafloor, is salt. The ocean contains about 35 grams of salt in every kilogram of seawater. If you were to take all of the salt out of the ocean and spread it evenly across every landmass on Earth, it would form a layer more than 40 stories thick. That salt has been accumulating for billions of years, carried to the sea by rivers washing over rock, a mineral record of everything the rain has touched. So here we are, floating at the edge of something vast. 71% of the world. Depths that swallow mountains. Darkness that swallows light. Currents that take 1,000 years to complete one quiet lap of the globe. And enough salt to bury entire cities. The ocean is extraordinary. And we've only just begun. Let your breathing slow. Let your body grow heavy and warm. We have a long, gentle journey ahead of us, and there is no rush at all. The ocean has been here for 4 billion years. It can wait for you to fall asleep. Let's go a little deeper. We left off at the edge of the sunlit world, that bright warm upper layer of the sea where light still reaches and the water still shimmers. But tonight, we're going to let ourselves sink a little further. Not quickly. Slowly, the way a leaf falls through still air. Down, and gently down. As we descend, the color drains from the world around us. Red fades first, it's the longest wavelength of light, and the water absorbs it almost immediately. Then orange. then yellow. By the time you're 30 meters down, the world around you is almost entirely blue and green. By 100 meters, it's a deep, dim twilight. And beyond 200 meters, the edge of the sunlit zone we talked about before, the blue fades to black. This middle layer, stretching from 200 meters down to around 1,000, is called the twilight zone. It's one of the largest habitats on Earth, and one of the least understood. The pressure here is already immense. Every 10 meters of depth adds roughly the weight of an entire atmosphere pressing in from all sides. At 500 meters down, the pressure on your body would be 50 times what you feel on the surface. The ocean does not give up its secrets easily. But here is the thing that makes the twilight zone so quietly magical. It glows. Not with sunlight, there is none of that left, but with life itself. Bioluminescence, the ability of living creatures to produce their own cold, chemical light, is one of the ocean's most breathtaking secrets. And it is far more common than most people realize. Scientists estimate that around 76% of deep-sea creatures are capable of producing their own light. In the darkness of the twilight zone and below, bioluminescence isn't the exception. It's almost the rule. The light comes in blues and greens, mostly, wavelengths that travel furthest through seawater. Some creatures use it to attract prey, dangling a glowing lure in the dark like a tiny, living lantern. Some use it to confuse predators, flashing suddenly to startle and disorient. Some use it to communicate, pulsing messages through the black water in patterns we are only beginning to understand. And some, perhaps most wonderfully, seem to use it simply as camouflage. A creature in the twilight zone faces a particular problem. If something is swimming below you, looking upward, it will see you as a dark silhouette against the faint glow of light filtering down from above. You are visible. You are vulnerable. And so some animals, certain fish, certain squid, have evolved rows of tiny light-producing organs along their undersides, which they use to match the dim light from above, making themselves nearly invisible from below. They are cloaked in their own light, hidden by brightness in a world of dark. One of the most extraordinary creatures in this world is the anglerfish. The females, the ones you've likely seen in illustrations, are remarkable things. They carry a bioluminescent lure on a long filament that extends from their foreheads, dangling in front of their wide, tooth-filled mouths like a fishing rod. They are patient hunters, hovering in the cold dark, waiting for something curious enough to swim toward the light. But what makes the anglerfish truly astonishing is what happens when they mate. The males are tiny, sometimes 100 times smaller than the female, and they have one purpose. When a male finds a female, he bites into her side. And then, slowly, their tissues fuse together. Their circulatory systems merge. He becomes, in the most literal sense, a part of her, providing sperm in exchange for sustenance, no longer a separate creature but a permanent attachment. A single female can carry several males fused to her body at once. It is one of the strangest, most intimate arrangements in the entire animal kingdom. The deep ocean is full of arrangements like this. Creatures that have solved the problems of survival in ways that seem almost impossible from where we sit on dry land. Take the pressure itself. At the very bottom of the Mariana Trench, the pressure is more than 1,000 times what we experience at sea level. It is the equivalent of having 50 jumbo jets stacked on top of you. And yet, creatures live there. Small shrimp-like animals called amphipods have been found at the very deepest points, scuttling along the seafloor in the crushing dark. Fish have been filmed at depths below 8 kilometers, drifting placidly as though the weight of the entire ocean above them were nothing at all. These creatures survive because their bodies are built differently from ours. Rather than rigid bones and air-filled lungs, they have soft, flexible structures, and their cells contain special molecules, piezolites, that stop proteins from being crushed and distorted by extreme pressure. Life, as it so often does, found a way not just to survive in the deep, but to belong there. To be perfectly, beautifully suited to a world that would kill us in seconds. And there is one more thing worth knowing about the deep ocean, before we rest here for a while. It is not silent. We sometimes imagine the ocean floor as a still and noiseless place, remote, cold, undisturbed. But the ocean is full of sound. Sound travels nearly 5 times faster through seawater than through air, and it travels far. The great whales have known this for millions of years. Blue whales, the largest animals ever to have lived on Earth, produce calls so low in frequency and so powerful that, before human noise filled the seas, they could communicate with one another across entire ocean basins. One whale, singing off the coast of one continent, heard by another whale near a different continent entirely. The ocean was their telephone, and it stretched across the world. That image, two blue whales, thousands of miles apart, somehow in conversation through the dark water between them, is one of the most quietly moving things about the sea. Let it sit with you as you breathe. The ocean is not empty. It is not silent. It is teeming, glowing, humming, even in its deepest, darkest corners. Especially there, perhaps. Sink a little further. Let your thoughts grow soft and slow, like something drifting downward through still water. We still have so far to go. Not all the way to the surface, not yet. But up, slowly, through the dark and into the dim, and then into the blue, and then into the light. Back through the twilight zone, back through the colors returning one by one. Green first, then yellow, then orange, then finally red, bleeding back into the world as we approach the surface. We're going somewhere warm now. Somewhere full of color and life and movement. Somewhere that, despite covering less than 1% of the ocean floor, is home to roughly 25% of all known marine species. We're going to the coral reef. Coral reefs are often called the rainforests of the sea, and it's a comparison that earns its place. Both are ancient. Both are extraordinarily rich with life. Both are built not by a single creature, but by countless lives layering themselves on top of one another over vast stretches of time. And both, quietly and urgently, are in trouble. But we'll come to that gently, in a moment. First, what is coral, exactly? It's a question worth sitting with, because coral is one of those things that looks like one thing and turns out to be something else entirely. Coral looks like rock, or plant, or perhaps some strange mineral formation in vivid colors. But coral is an animal. Or rather, it is thousands of tiny animals, each one called a polyp, living together in vast colonies. Each polyp is soft-bodied, no bigger than a pencil eraser, and it secretes a hard calcium carbonate skeleton around itself as protection. When it dies, that skeleton remains. The next generation builds on top of it. And the next. And the next. Over hundreds and thousands of years, those tiny skeletons accumulate into the enormous, intricate structures we call reefs, some of which are visible from space. The Great Barrier Reef, off the coast of Australia, is the largest living structure on Earth. It stretches for more than 2,300 kilometers, longer than the entire Great Wall of China. It is so large that it has its own postcode. And it is built entirely by creatures you could hold in the palm of your hand. But the coral polyp does not build alone. Living within the tissues of each polyp are microscopic algae called zooxanthellae. This relationship is one of the great partnerships of the natural world. The algae photosynthesize. They take in sunlight and produce energy, and they share that energy with the coral, providing up to 90% of the coral's nutritional needs. In return, the coral gives the algae a safe, sheltered home and a steady supply of carbon dioxide to fuel their photosynthesis. Neither could thrive without the other. And it is the zooxanthellae that give coral its color. Those vivid reds, yellows, purples, and oranges you see in reef photographs, almost none of that comes from the coral itself. It comes from the millions of tiny algae living inside it. When the ocean becomes too warm, even by just 1 or 2 degrees above average, the coral becomes stressed. And when it's stressed, it expels its zooxanthellae. Without the algae, the coral loses its color, and what's left behind is the stark white of bare calcium skeleton. This is coral bleaching. The coral isn't dead, not yet, but it is starving. If the water cools quickly enough, the algae may return. If it doesn't, the coral will die. It is quietly devastating, a relationship of millions of years, undone by a single degree. But tonight, let's imagine the reef as it is at its most alive. A healthy reef at dusk is one of the most extraordinary spectacles on the planet. Fish move through it in drifts of color: parrotfish, wrasse, butterfly fish, angelfish, darting between the branches and canyons of coral like birds through a forest canopy. Octopuses tuck themselves into crevices, watching everything with their strange, intelligent eyes. Moray eels hang from gaps in the rock, their mouths opening and closing in a way that looks threatening but is really just breathing. And once a year, on a night timed to the phase of the moon and the temperature of the water, something extraordinary happens across much of the Great Barrier Reef all at once. The corals spawn. Every polyp releases tiny bundles of eggs and sperm simultaneously, So many of them, from so many corals across such a vast area, that the ocean fills with a blizzard of pink and white. It looks, from underwater, like a snowstorm falling upward. The bundles drift to the surface, where they break apart, and the eggs and sperm find each other in the open water. It lasts for just a few nights each year, usually in November or December, and then it's over, and the reef goes quiet again, and somewhere in the water, new coral has begun. Above the reef, the ocean connects to something much larger. The sea, it turns out, doesn't just contain weather, it creates it. The ocean absorbs enormous amounts of heat from the sun, and it releases that heat slowly back into the atmosphere, moderating temperatures across the entire planet. Coastal cities are warmer in winter and cooler in summer than inland cities at the same latitude, because the sea beside them acts like a vast thermal buffer, smoothing out the extremes. The ocean is, in a very real sense, Earth's thermostat. And it doesn't stop there. Something like 50% of the oxygen in every breath you take was produced not by trees, not by forests, but by the ocean. Specifically, by the microscopic phytoplankton floating in the sunlit surface waters, tiny, plant-like organisms so small that millions of them fit in a single drop of seawater, yet collectively responsible for half the oxygen on Earth. Every second breath you draw in tonight came from the sea. Breathe that in for a moment. The ocean gave you this breath. And this one. And this one. It has been doing so, quietly and without acknowledgement, for as long as there have been lungs to fill. The reef shimmers below us. The polyps close their tiny mouths for the night. The fish find their sleeping places among the coral branches. And the phytoplankton drift at the surface above it all, still working, still breathing for you, in the dark. Your breathing has slowed. The world on the other side of your eyelids has grown distant and soft. Let it stay there. There's nothing you need to do right now, nowhere you need to be. Just the ocean, and this voice, and the dark water all around you. Let's talk about the giants. Every ocean on Earth has them, creatures of such scale that they seem to belong to a different world than the one we walk through on land. And in a way they do. The sea allows for a size that land simply cannot support. On land, every kilogram of body weight must be carried by legs and bones, fighting gravity with every step. But in water, that weight is supported by the sea itself. Buoyancy lifts you. Gravity loses its grip. And so, freed from that constraint, ocean life has grown to proportions that feel almost mythological. The largest animal ever known to have lived on Earth is alive right now. Not in the fossil record. Not extinct. Alive, and swimming, somewhere in the ocean tonight. The blue whale. A fully grown adult can reach 30 meters in length, longer than 2 buses parked end to end. It can weigh as much as 200 tons. Its heart alone is the size of a small car, and it beats so slowly, sometimes as few as 2 beats per minute when the whale dives deep, that you could count the seconds between each pulse. A blue whale's heartbeat has been recorded from over 2 miles away. The sound travels through the water like a slow, enormous drum. And yet, for all their size, blue whales survive on some of the smallest creatures in the sea. They feed almost entirely on krill, tiny, shrimp-like animals, each one barely the length of your little finger. A single blue whale can consume up to 40 million krill in a single day. It lunges through swarms of them with its mouth open wide, takes in an enormous gulp of water and prey, then pushes the water out through its baleen plates, long, brush-like filters that hang from its upper jaw, and swallows what remains. The largest animal on Earth, sustained entirely by some of the smallest. There is something deeply calming about that. Something that reminds you that scale isn't everything. That small things, in their multitudes, can sustain almost anything. Blue whales can live for over 90 years. Some of the whales swimming in the ocean tonight were born before the Second World War. They have crossed these same waters for nearly a century, following the same ancient routes their mothers taught them, holding maps of the ocean in their minds that we are only beginning to understand. But the blue whale, for all its magnificence, is not the oldest story in the sea tonight. Consider the Greenland shark. It is not a dramatic creature, not in the way that great whites or hammerheads are dramatic. It moves slowly, barely faster than a gentle walk, through the cold, dark waters of the North Atlantic and Arctic Ocean. It is gray and heavy-bodied, with small eyes that are often partially eaten away by a parasitic crustacean that attaches itself to the cornea. It is not beautiful, in any conventional sense. But the Greenland shark may be the oldest living vertebrate on Earth. Scientists age Greenland sharks by examining the radiocarbon dating of proteins in their eye lenses, tissue that forms at birth and never changes. And what they've found is extraordinary. Some Greenland sharks are estimated to be over 400 years old. One individual was estimated to be around 500 years old, which means there may be Greenland sharks swimming in the Arctic right now that were born before Shakespeare wrote his plays, before the Mayflower sailed, before the modern world, as we know it, existed at all. They reach sexual maturity at around 150 years of age. They are in no hurry. The cold, deep ocean asks nothing of them but patience, and patience is something they have in extraordinary abundance. Patience, it seems, is the ocean's greatest gift to its creatures. Take the sea turtle. Sea turtles have been navigating the world's oceans for more than 100 million years. They watched the dinosaurs rise. They watched them fall. They crossed paths with creatures that no longer exist, in oceans that no longer look the same, and they kept swimming. Today, 7 species of sea turtle remain, and they carry within them one of the most remarkable navigational abilities in the natural world. When a female sea turtle hatches on a beach, drawn immediately toward the ocean by the brightness of the horizon over the water, she imprints on the magnetic signature of that exact stretch of coastline. The Earth's magnetic field varies subtly from place to place, and the turtle memorizes the unique magnetic fingerprint of her birth beach. Then she swims away, into the open ocean, and may spend decades at sea, traveling thousands of miles across multiple ocean basins. And then, when she is ready to lay her own eggs, she navigates back. Across years and miles and open water, guided by a magnetic map she has carried since the day she hatched, she finds her way home, often to within a few kilometers of the exact beach where she was born. Not because anyone taught her. Not because she can see it or smell it from across the ocean. But because the Earth itself told her where she came from, and she never forgot. There are loggerhead sea turtles alive right now who have made this journey 5, 6, 7 times across their long lives. Crossing the Atlantic. Reading the invisible lines of the Earth's magnetic field the way you might read a road sign. Coming home. The ocean is full of homecomings like this. Full of creatures making journeys so vast and so faithful that they feel, when you learn about them, like something more than instinct. They feel like devotion. Let that word settle somewhere in you, devotion, as your body grows heavier and your thoughts grow softer. The blue whale is out there tonight, its great slow heart beating in the deep. The Greenland shark moves through the cold Arctic water, unhurried, ancient, unbothered by centuries. And somewhere on a warm, dark beach, or somewhere in the middle of a vast ocean, a sea turtle is following the Earth's own map home. The world is so much older and larger and more faithful than we sometimes remember. And you are held, tonight, by something that has been here for 4 billion years. Let go. Let the water hold you. The ocean has been patient with us tonight, the way it has always been patient. It was here long before the first human being stood at its edge and looked out across the water, wondering what was on the other side. And what a moment that must have been, that first encounter between a human mind and the open sea. The horizon stretching away in every direction. The water too wide to see across. The unknown, made visible. We have been drawn to the ocean ever since. For most of human history, the sea was not an obstacle. It was a road. The earliest seafarers, the Austronesian peoples of Southeast Asia, began spreading across the Pacific Ocean at least 5,000 years ago, navigating between islands in hand-built canoes with no instruments, no maps, no compass. What they had instead was something more intimate and more extraordinary, a deep, embodied knowledge of the sea itself. They read the stars, yes. But they also read the waves. Ocean swells travel vast distances from the storms and winds that create them, and they move in consistent directions for thousands of miles. An experienced Polynesian navigator could lie down in the bottom of a canoe, close their eyes, and feel the pattern of swells passing beneath the hull, distinguishing between swells arriving from different directions, detecting the subtle ways that islands interrupt and redirect those swells from hundreds of miles away. They could feel land before they could see it. The ocean spoke to them through the wood of the boat and the movement of the water, and they had learned, over generations, to listen. Using these techniques, Polynesian navigators settled nearly every habitable island across the vast Pacific, an ocean that covers more area than all of Earth's landmasses combined. They reached Hawaii. They reached New Zealand. They reached Easter Island, one of the most remote inhabited places on Earth, more than 2,000 miles from the nearest populated land. They did it in open boats, guided by the sea itself. It is one of the greatest feats of exploration in all of human history, and for a long time, the Western world barely knew it had happened. Closer to home, or to what many of us think of as the center of history, the Mediterranean Sea was the cradle of civilizations. The Phoenicians sailed it and built trade networks that stretched from the Middle East to the coast of Britain. The Greeks mapped its shores and told stories about its monsters. The Romans called it Mare Nostrum, our sea, and built an empire on the ability to move soldiers and grain across its waters quickly and reliably. For centuries, whoever controlled the Mediterranean controlled much of the known world. But the ocean that perhaps changed human history most dramatically is the Atlantic. For a long time, European sailors believed the Atlantic was the edge of the world, or close to it. There were maps, drawn in the medieval period, that showed sea monsters crowding the western horizon, a cartographer's way of saying, "Here, we do not know. Here, things may devour you." The ocean was the limit of the imaginable world. And then, in 1492, Christopher Columbus sailed west from Spain and didn't fall off the edge. What he found instead set in motion 500 years of history that reshaped every continent on Earth, for better and for worse, in ways still felt today. The ocean didn't just connect the old world and the new. It became the channel through which empires, diseases, peoples, languages, plants, animals, and ideas flowed in both directions, transforming everything they touched. The Atlantic carried more than trade. It carried, in its darkest chapter, the transatlantic slave trade, an estimated 12.5 million people forcibly transported across the ocean between the 16th and 19th centuries. The ocean that had once been the edge of the imaginable world became, for millions of human beings, a crossing of unimaginable suffering. The sea holds that history too, in its depths. We do not look away from it. But the ocean has also carried wonder. It carried James Cook, who mapped the Pacific coastlines with a precision that astonished the world. It carried Ernest Shackleton, whose ship was crushed by Antarctic ice in 1915, and who then sailed an open lifeboat 800 miles across the most violent ocean on Earth to find help for his stranded crew, a journey of such audacity that it remains almost incomprehensible. It carried Thor Heyerdahl, who in 1947 sailed a balsa wood raft from Peru to Polynesia to prove that ancient peoples could have made the same crossing, and who did it, in part, out of a refusal to believe that the ocean was ever truly a barrier to the human spirit. These stories share something: a willingness to look at the horizon and choose it, to sail toward the unknown not because the outcome was certain, but because the sea was there, and it was calling. We are landlocked creatures, by biology. We cannot breathe underwater. We cannot survive in the cold of the deep. We have no fins, no echolocation, no magnetic map. And yet we have always gone to the ocean. We have built boats from reeds and balsa wood and oak and steel. We have drawn maps and written myths and named the currents and the capes and the uncharted waters. We have stood at the shore in every century, on every continent, and felt the same pull. The ocean calls to something older than thought. Something in us that recognizes it, the way you sometimes recognize a place you've never been, as if your body knew it before your mind did. You are made of water, about 60% of you by weight. The salt concentration in your blood is strikingly similar to the salt concentration of the sea. Some scientists have described this as a kind of echo of our origins, life beginning in the ocean, carrying a little of it with us when we eventually came ashore, hundreds of millions of years ago. Perhaps that is why the sound of waves is so reliably soothing. Why standing at the shore feels like arriving somewhere. Why the ocean, in almost every culture on Earth, features in the oldest stories, as a source of life, a place of mystery, a passage between worlds. You have come from the sea, in the longest sense of that phrase. And tonight, it is carrying you somewhere quiet. I can tell, because the world has gone quieter around you. The thoughts that were busy and bright when you first lay down have softened. They're not gone, perhaps, but they've lost their edges. They've become more like clouds than stones. And the ocean is still here, still moving, still breathing all around you. Let's talk about that breathing. The ocean and the atmosphere above it are not separate things. They are partners, two halves of a single planetary system, passing heat and water and gases back and forth between them in an endless conversation that has been going on for billions of years. And it is this conversation, more than almost anything else, that makes Earth the way it is. That keeps it warm enough for life, wet enough for rivers, stable enough for civilizations to be built and to last. The ocean breathes water into the sky. Every day, an enormous amount of water evaporates from the ocean's surface, lifted by heat and wind into the atmosphere, where it forms clouds and eventually falls again as rain or snow. Around 86% of all evaporation on Earth comes from the ocean. The rain that falls on your roof, the snow that settles on mountain peaks, the rivers that carry fresh water across continents. Almost all of it began as ocean water, lifted invisibly into the air and carried by the wind to where it was needed. The ocean is the source of nearly all the fresh water that makes land life possible. Think about that the next time you drink a glass of water. It has almost certainly been part of the ocean before. Perhaps many times. But the ocean doesn't just move water. It moves heat. The sun doesn't warm the Earth evenly. The tropics receive far more solar energy than the poles, and if nothing redistributed that heat, the equator would be uninhabitably hot and the poles would be far colder than they already are. The ocean is one of the two great systems, along with the atmosphere, that takes heat from where there is too much and carries it to where there is too little. It does this through currents. We talked in our first segment about the global ocean conveyor belt, that vast, slow circulation of water that takes roughly 1,000 years to complete one loop around the planet. Part of that system is the Gulf Stream, a powerful current that carries warm water from the Gulf of Mexico northeastward across the Atlantic, releasing heat into the atmosphere as it goes. That heat is what gives Western Europe its unusually mild climate. London sits at roughly the same latitude as Calgary in Canada, or parts of Siberia, places with brutal winters and short summers. But London has daffodils in February and rarely sees serious snow, because the Gulf Stream delivers warmth across the water. The ocean keeps it gentle. The ocean also shapes weather in more dramatic ways. Hurricanes, called typhoons in the Pacific, cyclones in the Indian Ocean, but the same phenomenon wherever they occur, are born over warm ocean water. When the sea surface temperature rises above about 26 degrees Celsius, it begins to evaporate water so rapidly that the rising warm, moist air creates a column of low pressure. Air rushes in from all sides to fill that low pressure, and the rotation of the Earth, the Coriolis effect, sets that rushing air spinning. The spin tightens and accelerates, feeding on the heat and moisture of the ocean below it, building into a vast rotating storm that can stretch for hundreds of miles and carry winds strong enough to flatten forests and push walls of water tens of feet high onto coastlines. Hurricanes are terrifying things. But they are also, in their way, the ocean doing its job, redistributing heat, moving energy from the warm tropics toward the cooler latitudes, doing what the planet asks of it. And when those storms pass, the ocean is still there, patient, unchanged in any fundamental way. Storms cross it and fade. Ships cross it and disappear into history. We have watched from its shores for thousands of years, frightened sometimes, awed always, and the ocean has never once acknowledged the watching. There is something in that which is deeply restful. The ocean's indifference is not cold. It's simply vast. You cannot trouble something that contains more than 1.3 billion cubic kilometers of water. You cannot worry something that has weathered asteroid impacts and ice ages and the slow rearrangement of continents. You can only float on its surface and be grateful for the warmth it sends your way. Waves are another gift of that conversation between ocean and atmosphere. Most waves are born from wind. The wind blows across the surface of the sea and transfers energy into the water, creating ripples that build into swells that travel, sometimes for thousands of miles, across open ocean before they finally reach a shore and break. A wave you watch curling and crashing on a beach in Cornwall may have been born in a storm off the coast of Newfoundland, days earlier, carrying that energy silently across the Atlantic until it found land. And here is something strange and lovely about waves. The water itself doesn't travel with the wave. When a wave passes through the ocean, the water molecules move in circles, rising and falling as the wave passes, but returning almost exactly to where they started. It is the energy that travels, not the water. The wave is a shape, passing through the sea. The sea itself stays home. Only as a wave reaches shallow water and the ocean floor disrupts those circular movements, does the wave finally break, toppling forward, releasing all that stored energy in a rush of white water and sound. That sound, the sound of a wave breaking on a shore, is one of the most universally soothing sounds the human brain knows. Studies have shown that the rhythmic, broadband sound of surf, a mix of frequencies covering a wide range, regular but never exactly predictable, activates the brain's rest and digest response. It slows the heart rate. It reduces cortisol. It literally, measurably, relaxes you. There is science behind why you are here tonight, listening. The ocean has always known how to help you sleep. It has been sending waves to shore for 4 billion years, and every one of them has made that sound, and the sound has always meant the same thing. Here, rest. You are at the edge of something ancient and enormous. You are small and safe and held. Breathe with the wave. It's night out there. Not just where you are, out on the ocean too. The sun has gone down over the water, and the surface has turned dark, reflecting whatever stars are overhead, shifting and glimmering and breaking apart with each small wave. If you were standing on the deck of a ship in the middle of the ocean tonight, far from any coast, far from any city, the sky above you and the water below you would both be full of light, starlight above and something else below. Something alive. The ocean at night is not the same ocean as the day. It transforms. The creatures that spent the daylight hours hiding in the deep, tucked into the cold and the dark where predators couldn't easily find them, begin, as the sun goes down, to rise. This is called the Deal vertical migration, and it is the largest daily movement of animals on Earth. Every night, across every ocean on the planet, billions upon billions of small sea creatures, tiny fish, squid, copepods, krill, jellyfish, and countless others, ascend from the depths toward the surface, drawn upward by darkness and the promise of food. They spend the night feeding in the rich, plankton-filled surface waters. And then, as dawn approaches, they descend again, back into the deep, before the light returns and the larger predators that hunt by sight become dangerous again. This migration happens simultaneously across the entire ocean, every single night, without pause. It has been happening for hundreds of millions of years. It is so vast and so consistent that in the early days of sonar technology, during the Second World War, naval operators were baffled by a deep layer that appeared on their screens each evening, rising toward the surface, and sinking again by morning. They called it the deep scattering layer, and for some time they genuinely weren't sure what it was. The answer, when it came, was almost comic in its scale. It was animals. Just animals, going about their nightly business. So many of them, so densely packed, that they reflected sonar signals back like a false ocean floor. On the surface, the night brings its own kind of magic. In certain sheltered bays and lagoons around the world, in Puerto Rico, in Jamaica, in the Maldives, along some coastlines in Australia, the water itself seems to glow at night. Dip your hand in and it lights up around your fingers. Swim through it and your body leaves a trail of cold blue fire. Wade in and every footstep blooms with light. This is bioluminescence at the surface, caused most often by microscopic organisms called dinoflagellates. These single-celled creatures produce light through a chemical reaction when they are physically disturbed, when a wave moves them, when a fish swims through them, when your hand passes through the water. A single dinoflagellate produces just the tiniest, most infinitesimal flash of light. But in a bay where millions of them are packed into every cubic meter of water, the cumulative effect is extraordinary. The water lights up as if something electrical is moving through it, as if the ocean is thinking, and you can see its thoughts. Some of these bioluminescent bays, called biobays, are so densely populated with dinoflagellates that the water appears almost cloudy in daylight, tinged faintly red or brown from the sheer number of organisms. But at night, they become something else entirely. Something that defies easy description. Something that people who have seen it tend to remember for the rest of their lives. Puerto Rico's Mosquito Bay, on the island of Vieques, is often cited as the brightest biobay in the world. The conditions there are particular: warm, shallow, sheltered water, rich in the nutrients the dinoflagellates need, with a narrow channel that limits how much of the population flows out to sea each day. The result is a concentration of bioluminescent life so intense that the water glows visible blue even from the air. Kayakers paddle through it at night in silent wonder. Every stroke of the paddle writes light into the water. The night ocean is also the domain of the nautilus. The nautilus is one of the ocean's true living fossils, a creature whose basic body plan has remained almost unchanged for 500 million years. It survived the extinction event that killed the dinosaurs. It survived the ice ages. It drifts through the deep water of the Pacific and Indian Oceans in its elegant, chambered shell, a shell built in a spiral so mathematically precise that it has become one of nature's most famous examples of geometric beauty. The nautilus doesn't know this, of course. It is simply growing the way it has always grown, adding new chambers to its shell as it matures, sealing the old ones off and filling them with gas to control its buoyancy, rising and sinking through the water with the same unhurried grace it has practiced for 500 million years. It has no bones, no spine, just soft flesh, tentacles, and that ancient, perfect shell. It sees poorly, navigates by smell and by memory, and lives a life of extraordinary patience, surfacing at night to feed, descending again in the day, following a rhythm as old as the ocean itself. And while the nautilus drifts, and the dinoflagellates glow, and the great vertical migration moves in its slow billions through the dark water, something else is happening on the surface. The ocean at night reflects the sky in a way that has guided human beings for as long as we have sailed. The stars above and the stars reflected below. A sailor in the open ocean on a clear night is surrounded on all sides by light, floating between two skies. Polynesian navigators, those extraordinary wayfinders we talked about earlier, use stars not just as fixed points of reference but as a kind of dome of knowledge, memorizing the rising and setting points of hundreds of individual stars across the horizon, building a map of the entire sky that they could read in any direction, at any time of night, in any season. One star, Hoculae, the star we call Arcturus, rises almost directly over Hawaii. For Polynesian navigators sailing northward toward the islands, that single star, rising at just the right point on the horizon, was the signal that they were on course. A star as a lighthouse, the sky as a map, and beneath it, the dark ocean, full of creatures rising and glowing and drifting and diving, doing what they have always done, what they will always do, long after the last sailor has read the last star home. The night ocean is ancient and alive and full of quiet purpose. You've come so far tonight, deeper and quieter and further from the busy world than you were when we began. The ocean has been carrying you, the way it carries everything, eventually, and you are somewhere very still now, somewhere very soft. Let's go somewhere few people ever think to look. We spend so much time looking at the surface of the ocean, at the waves, at the horizon, at the light on the water. And we spend some time thinking about what swims through it, the whales and the sharks and the turtles and the glowing things in the deep. But underneath all of that, underneath the water and the creatures and the darkness, there is a landscape. A vast, extraordinary, largely unseen landscape of mountains and valleys and plains and volcanoes that makes the geography of dry land look almost modest by comparison. The ocean has a floor. And the floor is astonishing. Running down the middle of the Atlantic Ocean, from the Arctic all the way to the southern tip of the globe, is a mountain range called the Mid-Atlantic Ridge. It is the longest mountain range on Earth, stretching for roughly 17,000 kilometers, longer than the Andes and the Rockies and the Himalayas combined. And almost none of it has ever been seen by human eyes, because almost all of it lies 2 kilometers or more beneath the surface of the sea. The Mid-Atlantic Ridge exists because the ocean floor is not still. Beneath it, the tectonic plates that make up the Earth's crust are slowly moving, and in the middle of the Atlantic, 2 plates are pulling apart from each other, at roughly the speed your fingernails grow. As they separate, molten rock wells up from below, filling the gap and cooling into new seafloor. The Atlantic Ocean is getting wider. Not quickly, just a few centimeters per year. But steadily, year after year, century after century, the 2 sides of the Atlantic are drifting apart, and new ocean floor is being born along that underwater ridge as they do. This means that the youngest rock on Earth's surface is found in the middle of the ocean. And the oldest oceanic rock is found at the edges, where the plates have been slowly pushing old seafloor down beneath the continents in a process called subduction. The old ocean floor recycled back into the Earth's interior, melted down, ready to rise again somewhere else. The ocean floor is constantly renewing itself. It has been doing so for hundreds of millions of years. The seafloor you would walk on, if you could, has not been there for nearly as long as the continents. It is, in geological terms, quite new. Along the Mid-Atlantic Ridge, and along similar ridges in the Pacific and Indian Oceans, the volcanic activity that drives all of this creates one of the ocean's most extraordinary environments. Hydrothermal vents. Imagine a crack in the ocean floor, far down in the dark. Seawater seeps into that crack, down through the rock, closer and closer to the heat of the Earth's interior. It heats up to temperatures of 400 degrees Celsius or more. At that temperature, on the surface, water would simply boil away into steam. But down here, under the crushing pressure of kilometers of ocean above, it cannot boil. It stays liquid. Superheated, mineral-rich liquid, which then forces its way back up through the seafloor and erupts from vents in great billowing plumes. The minerals in that superheated water iron, sulfur, copper, zinc, precipitate out as the water meets the cold ocean around it, forming tall chimneys of dark mineral deposits that can grow several meters high. The plumes of dark, mineral-laden water rising from these chimneys look exactly like smoke from a chimney, and so these structures are called black smokers. They are some of the strangest and most beautiful things on the seafloor. But the truly astonishing thing about hydrothermal vents is not the geology. It is the life. In 1977, scientists diving in the submersible Alvin near the Galapagos Islands discovered something that genuinely shook our understanding of life on Earth. Around hydrothermal vents, in water superheated by volcanic activity, in complete and permanent darkness, with no sunlight whatsoever, they found entire ecosystems, thriving, complex, abundant communities of living things. Tube worms up to 2 meters long, giant white clams, blind shrimp, ghostly crabs, all of them clustered around the vents in densities that rivaled the richest coral reefs. None of these creatures depended on sunlight. None of them were part of the food chain that begins with photosynthesis, the chain that supports almost every other ecosystem on Earth. Instead, they were supported by chemosynthesis, bacteria that extract energy not from light, but from the chemical reactions between the superheated vent water and the cold ocean. The bacteria form the base of the food chain. The tube worms host billions of them inside their bodies, living off the energy they produce. Everything else feeds on something that feeds on something that feeds on those bacteria. Life, it turned out, did not need the sun. This discovery changed everything. Because if life can exist without sunlight, sustained entirely by heat and chemistry from within the Earth itself, then the range of places in the universe where life might exist expanded enormously. The moons of Jupiter and Saturn, Europa, and Enceladus, are thought to have liquid oceans beneath their icy surfaces, kept liquid by the heat of tidal forces rather than sunlight. Before 1977, it was hard to imagine what could live in such places. After 1977, we had a template. The tube worms around hydrothermal vents may be the closest thing on Earth to life as it might exist on another world. And they live in your ocean. Right now, clustered around cracks in the seafloor, in the dark, sustained by the heat of the Earth's own interior, waving their feathery red plumes in the warm current of superheated water rising from below. The ocean contains multitudes. It contains mountain ranges longer than anything on land. It contains volcanoes building new seafloor every day. It contains ecosystems that run on chemistry rather than sunlight, and creatures that have never seen the sky and never will, and yet are perfectly, completely alive. There is more world down there than most of us will ever fully grasp. And perhaps that is part of what makes the ocean so restful to think about, as you lie here in the dark. It is so much larger than any problem you are carrying. It contains so much more mystery than any question keeping you awake. You've traveled so far tonight, further than you probably realize. From the sunlit surface to the deepest trench. From the glowing bays to the volcanic vents. From the first explorers who read the waves with their bodies to the tube worms that have never needed the sun. You have crossed the whole ocean, in your mind, in the dark, and it has been carrying you all along toward this one quiet place. The top and bottom of the world. Let's go somewhere very cold now. Very still. Very white. The polar oceans, the Arctic in the north, the Southern Ocean ringing Antarctica in the south, are unlike any other water on Earth. They are cold in a way that is difficult to fully imagine from a warm room. The surface water in the Arctic can reach minus 1.8 degrees Celsius, below the freezing point of fresh water, kept liquid only by its salt content. The Southern Ocean is similarly frigid, whipped by the strongest sustained winds on Earth, generating waves that travel endlessly around the continent with nothing to slow them down. No land, no barrier, just open water all the way around the bottom of the world. These are not gentle places. And yet, life here is not sparse. It is, in certain ways, more abundant than almost anywhere else in the ocean. The cold water of the polar seas holds more dissolved oxygen than warm water does. Cold liquids can hold more gas, the same way a cold fizzy drink holds its bubbles longer than a warm one. And that oxygen, combined with the nutrients that well up from the deep in these regions, creates conditions for explosive blooms of phytoplankton in the summer months, so vast they can be seen from space, turning the surface of the sea green and blue-green for hundreds of miles. Those blooms feed krill. The krill feed almost everything else. In the Southern Ocean, Antarctic krill form swarms so dense and so enormous that they too can be seen from space, reddish-pink patches spread across the water's surface, billions upon billions of the small translucent creatures moving together in a mass that can weigh more than the entire human population of Earth. They are the engine of the Antarctic ecosystem. Penguins eat them. Seals eat them. Seabirds eat them. And the great whales, the blue whales, the humpbacks, the fin whales, travel thousands of miles each year to reach these waters and feed on them. Everything in the Southern Ocean leads back to krill. But tonight, let's linger on the ice itself. Sea ice is one of the ocean's most important and most beautiful features. Every winter, as temperatures drop, the surface of the polar oceans begins to freeze. Not all at once. It starts with tiny ice crystals forming in the water, a thin, greasy layer called frazzle ice, which gradually thickens and consolidates into pancake ice, circular plates of ice with raised edges, formed by the gentle collision of pieces as the water moves, and eventually into the solid sheets of pack ice that cover millions of square kilometers of the polar seas in winter. At its maximum winter extent, Arctic sea ice covers an area roughly the size of the United States. It transforms the ocean into something that looks more like a landscape, a vast, white, wind-scoured plain broken by ridges and channels and the occasional open lead of dark water. It is disorienting from above because it looks like land. But underneath it, the ocean continues. Cold and dark and alive. Under the sea ice, in the thin layer where ice meets water, lives a community of life that few people know about. Algae grow on the underside of the ice, sustained by the faint light filtering down through it in summer, turning the ice a faint brownish-green, visible if you were to chip a piece away and look at its underside. These ice algae are some of the first things to bloom in spring, ahead of the open-water phytoplankton, and they form an important early food source for the krill waiting below. The underside of sea ice is, in other words, a garden. An upside-down garden in the dark, tended by algae and grazed by krill, hanging from the ceiling of a frozen world. In the Arctic, the animal that has adapted most completely to this frozen world is the polar bear. Polar bears are, biologically, marine mammals, classified as such because they depend on the sea for their survival. Their primary prey is the ringed seal, and they hunt by waiting, with almost incomprehensible patience, at holes in the sea ice where seals must surface to breathe. A polar bear can wait at a breathing hole for hours. Sometimes longer. Perfectly still, perfectly quiet, the wind at their backs so their scent doesn't carry, just waiting for the moment the seal surfaces. Their fur, which appears white, is not actually white at all. Each individual hair is transparent and hollow, evolved to channel light down toward the dark skin beneath, which absorbs heat from the sun. A polar bear is, in a sense, wearing a coat of tiny optical fibers. The whiteness is structural, not pigmented, the same phenomenon that makes snow look white, even though individual snowflakes are also transparent. The ocean and its ice have shaped, over thousands of years of evolution, an animal that is part hunter, part solar collector, perfectly built for a world of ice and cold water and long, dark winters. At the other pole, the emperor penguin faces a different version of the same challenge. Emperor penguins breed in winter, the harshest, coldest, darkest winter on Earth, on the Antarctic sea ice, in temperatures that can drop to minus 60 degrees Celsius with wind chill. The males incubate the eggs alone for 2 months, standing in the dark, through blizzards and polar night, with a single egg balanced on their feet beneath a warm fold of skin. They eat nothing for those 2 months. They huddle together in groups of thousands, taking turns moving from the cold outside to the warm interior of the huddle, sharing their body heat in a slow, collective rotation. And then the egg hatches, and the female returns from the sea, where she has been feeding, and finds her mate among thousands of identical penguins by his voice alone. They know each other's calls. They have always known each other's calls. From the moment of pairing, they memorize them, the way you might memorize the voice of someone you love. The chick is born into the coldest place on Earth, in the darkest season, in the middle of a frozen ocean. And it is immediately found, and fed, and held. The ocean provides for even this. Even here.